Hi, what I'm going to tell you here is a version of the talk I gave at the Theoretical Physics Seminar of the Institute of Physics of Polish Academy of Sciences in Warsaw in January this year. And the motivation for this talk was this paper of mine, which was published in Acta Physica Polonica in January. And for me, it's an interesting story, so to say, because as you can see in the slide, we have 4 papers here. The first one is from 1988, and actually this is the first journal paper I've ever published in my whole career. And roughly in 2015, I noticed that some people start to publish on the archive certain ideas which are related to an idea or a trick, if you want, which I published in this paper in Physics Letters in 1988, and clearly those people are unaware of my contribution, so I thought that maybe I should post this old paper of mine on the archive. But then, of course, it was difficult, even impossible to do it, because first of all, I didn't have the LaTeX file. Secondly, when I read the paper, I didn't like it. So I liked the result, I liked the idea, but I didn't like the way it was written. It was really many years ago. So I decided that, okay, it is simplest if I just write again a version of this paper and just post it on the archive. So I did it. I invented new examples. But then, as it often happens, since I started to think again of this old problem, the problem started to live its own life, so to say. And at a certain moment, I decided that I have to really publish this paper, because I really have a new version of the whole thing. And I published in Foundations of Science in May 2020 this contribution. And then in this paper, I already announced that I'm able, on the basis of this formalism which I developed in the meantime, I'm able basically to produce a counterexample to Bell's theorem, which means that I'm able to formulate a hidden variable theory where we have ideal detectors, where observers have free will, where probabilities are non-negative. And first of all, it's local. So clearly, all the explicit assumptions which are present in the modern version of Bell's theorem are satisfied, and yet I can exactly reconstruct in this way, in this formalism, quantum probabilities typical of two-particle singlet state, which are exactly those probabilities which were used by Bell in his original paper. Now, of course, there is some mystery in it, but there is no cheating. And if I'm able to do it, it means that I have found a new hidden assumption in the proof of the Bell inequality, simply. So, using this assumption, which is which is a loophole in the standard terminology in the proof, I can circumvent the whole literature, so to say, on Bell's theorem. And this loophole is based on the following fact, namely, in Bell's construction, probabilities, quantum probabilities, are supposed to be reconstructed from a hidden variable theory, where we have certain space of hidden variables, and we have certain measure on this space, and we have certain integrals, we can say, on this space, and we have probability density of hidden variables, and integrals over these hidden variables should produce quantum probabilities. And the trick is that Bell apparently used the most general form of integration in his proof, whereas mathematics is richer. The some additional structures which can be employed, and in particular there are different types of integration which can be used. This integration which I'm using is the so-called non-Newtonian integration, and it goes back to works which I will mention later by Grossman and Katz from the end of 1960s, basically. So it's not, the very mathematical structure is not really exotic. It was unknown to Bell, of course, but today we know these structures, so we can use them. But because of this long story, which you can see in these publications here, I would like to use this occasion and tell you something about the prehistory of this problem. Because it didn't start for me in 1988, it started in 1980 or 81. And I would like to use this occasion to tell you something about this earlier stage. And it goes to a friend of mine, Andrzej Posiewnik, who was a person responsible for the fact that I became a theoretical physicist. Because I knew Andrzej from mountains, we were climbers, and he was already an experienced theoretical physicist at that time. And when I decided I would like to study physics, then Andrzej talked to me, we discussed my interests, and he said that definitely I should be a theoretical physicist, and therefore I started in 1979 I started theoretical physics at University of Gdańsk, and Andrzej was my unofficial tutor. Unofficial in the sense that formally I didn't have a tutor, but he was taking care of my education, and in particular he showed me very early books by David Bohm. And I think it was Andrzej also who showed me first publications on Bell's theorem, and I read those first papers by Henry Stapp, Eberhard, Asher Perez, I remember. And I was fascinated. I thought that I've never heard of anything so interesting. So I decided I have to understand Bell's theorem, but in order to understand, I first have to understand quantum mechanics, because I didn't know quantum mechanics. I didn't have it yet in my course. So I started to learn quantum mechanics in order to understand Bell's theorem. I was already at the second year of my studies, and it was in 1980, 1981, basically. And in fall 1981, the third year of studies, I started the official course of quantum mechanics. And this course the teacher was Ryszard Horodecki, and the exercises were led by Marek Żukowski. And therefore I would like to tell you an anecdote, which is the anecdote told once by Marek. Actually, what I'm going to show you is a fragment of his acceptance speech of his Hevelius Prize, which he got for his works on foundations of quantum mechanics. And he said those words. It was 2015, I believe. Yes, 2015. I used Google Translate to translate this quotation. I think it's a reasonable quotation. So indeed, it was when I started learning quantum mechanics, official course of quantum mechanics. As I said, I was already after a year of studies of Bell's theorem. I bought my own copy of David Bohm's quantum mechanics at that time, because I wanted to understand EPR paradox, and I knew that it's described in this book. So I used all the possible means to get to the book. So I bought it. And then I remember I asked Ryszard Horodecki, who was teaching this course, this is Ryszard, about Bell's theorem, and he said that what he didn't like about Bell's theorem at that time was that it's a theorem about relativistic physics, basically, or a theorem with relativistic ambitions, because it tells something about faster than light communication, locality, structure of space-time, and so on. But yet, it was formulated in the paradigm of non-relativistic quantum mechanics. So he said that if one really wants to seriously treat the subject, then one should first of all formulate Bell's inequality in relativistic quantum mechanics. So I decided that, okay, I found my first scientific problem and I started to work on it. But then, as Marek says, in 1981, the martial state was imposed in Poland and university was closed, actually, and I was arrested after a week and I spent a year in prison, basically. So I was learning this in prison, but Marek says here that it was during the martial state, this conversation we had, it must have been a little bit earlier, because during the martial state we didn't have classes because university was closed at that time, of course, so it must have been a few days or weeks before. But anyway, it was around probably December 1981. In 1984 I wrote my first paper, which I submitted to Physics Letters, and it was rejected. And then 2 years later I defended my master's thesis at University of Gdańsk, and it was about relativistic spin. Therefore, these results which I had for Bohm's Gedanken experiment, or Einstein-Podolsky-Rosenbaum thought experiment, could be included in my thesis in principle, but I was so frustrated by the reaction of the community that I was just afraid of including this result in my master thesis. So I decided I just quit. I don't want to go in that direction. But, well, okay, I'll come to it. Yeah, okay, so it was in 1981. I wrote the paper in 1984, but then in 1995, 10 years later, or 11 years later, by accident I found a simpler and more general version of this old result of mine from 1984. So I had this, I wrote it down, but I didn't even try to publish it. But then at a certain moment after my postdoc, I tried for a new position somewhere, and Bogdan Mielnik, this is Bogdan Mielnik, tried to help me, and he said that the problem with me is that I have too few publications. I have to have more publications, and therefore I should try to publish everything I have somewhere. So all results I have, I should try to publish. And he asked me what I have. I said, okay, I have this old result on relativistic Bell inequality, but it was submitted many years ago and it was rejected, and I basically gave up. And he said that okay, it's an interesting result. Probably nobody did anything like that before, so I should definitely try to publish it. So I wrote this paper, which finally was published in Physical Review A in January 1997. Here you can see the acknowledgement to my conversation with Ryszard Chorodecki, but this conversation with Ryszard was 16 years earlier. 16? 15 perhaps. Yeah. It was at the fall of 1981. Yeah. But let me go back to 1982. Yeah. I was indeed arrested. I was sentenced to 3 years of prison. I spent the whole 1982 in prison, and these, you can see here the copy, my own copy of David Bohm's textbook, and you have here the seal impression, the underground seal impression made by political prisoners in the Potulce prison in 1982. And here, this is the copy of the paper by Clauser and Shimony from Reports on Progress in Physics. which I had with me in prison actually, and it's the silly impression. It's still in the library of University of Gdańsk, so it's a kind of proof that I indeed worked on Bell's theorem as a student already in 1982. Now, before we go further, one more slide which I couldn't resist. I think that at that time I was in a good company, so to say, because YURI ORWOLF is a forgotten founding father of quantum information. This is a person who wrote, in my opinion, the first papers on Q-binary mathematics, so application of quantization of numbers, basically, numbers in the sense of mathematical analysis, like derivatives, for example. And as you can see, his affiliation here is prison camp 37. I think the camp was in Perm, the town in Urals. I was very impressed by this when I saw it. Well, I learned that ORWOLF died in September 2020. I learned while preparing these slides, so I had no occasion of talking to him. And yet, one more prehistoric aspect. This is a preprint by Marianne Kuczynski, which was written in ICTP in 1984 again. And I knew this paper from that time because in front of library, physics library of University of Warsaw, they had a table when they were putting various preprints, and in particular there was a whole collection of preprints from ICTP, and one could just take it, collect whatever you wanted. So I remember I found this paper by Kuczynski at that time. It was the time I was trying to write something myself, and I think Kuczynski is the first Polish physicist who really worked on Bell's theorem, and as you can see from this acknowledgement, he even collaborated with Bell himself when they worked together in CERN. Okay, now let's go back to our present situation. So we have 3 papers, actually we have 4 papers, as you can see, because it's unifying aspects of generalized calculus from entropy. It's a kind of review paper where certain generalizations of these results, which are here and here, can be found. But I will begin now with telling you what I don't like in the standard quantum mechanical approach to the Bell inequality or Bell's theorem. So, this quantum perspective. So, of course, there are many different ways of formulating Bell's theorem or an inequality a la Bell in quantum mechanics. There are many inequalities, and this is what I'm showing here is Clauser-Horn-Shimony-Holt inequality, which is kind of simple, which I will not finally use in my own construction because I prefer Clauser-Horn inequality, which I think is more fundamental, because this inequality mixes probabilities and averages, basically. So probabilities and eigenvalues of operators, or probabilities and values of random variables, whereas I think that at such a fundamental level one should rather concentrate just on probabilities, because probabilities are indeed measurable in experiments. One doesn't measure typically eigenvalues of operators, one just counts numbers, counts detections. So an experiment deals with probabilities, therefore it's better to use an inequality just based on probabilities. But moreover, it's irrelevant which inequality you prefer from my point of view, because what I'm going to show you is that I can formulate a hidden variable local hidden variable theory which just reconstructs exactly probabilities, quantum mechanical probabilities for a singlet state. So any inequality which is violated by a 2-bit or 2-qubit system is also violated in my approach. So it doesn't matter which inequality I'm using. I will reconstruct exactly the probabilities from quantum mechanics. But since if I'm not cheating and I can really reconstruct quantum probabilities in a local hidden variable way, there must be some reason why the argument of Bell does not apply. So there must be some reason why I'm not able to prove the Bell inequality. Any kind of Bell inequality which is violated by quantum mechanics in this context. So we have to understand it. Therefore, let's have a look, for example, at this Clauser-Horn-Shimony-Holt example. We have set an observable C, which is a matrix essentially, because it's a tensor product of 2 by 2 matrices, so it's a 4 by 4 matrix. Sigmas are Pauli matrices. It defines 4 random variables, A prime, B, and B prime. A and A prime are measured by Alice, one observer, and B and B prime are measured by another observer we call Bob. And here the second line, transition between the second and third line, involves something which I call locality. And locality means simply in this context that this A is the same A as this one. Or this A prime is the same A prime as this. The same means that the fact that it's multiplied by B does not influence A. So A is not influenced by the choice of B or B prime. In this sense, it is local. It would be non-local if this A would be dependent on B, and this A would be dependent on B prime, and so on. Therefore, in a non-local case, I cannot make this step, this transition from the second line to the third line. And I am not able then, in the non-local case, I am not able to continue the proof, and therefore I am not able to prove the inequality. Therefore, it is possible to violate this inequality. Violate, which means that to find a system for which this inequality does not apply. It is possible to do it if you have a non-local theory. But if you are able to make this transition, then you can continue with the proof and finally arrive at certain inequality, which we call Clauser-Horn-Shimony-Holt in this concrete context. So let's say, we have locality, which means that since this A and this A is the same A, I can write this formula, apparently obvious formula. Yeah? Also here. In this way, I introduce certain observable corresponding to Bob, namely B plus B prime, and another one, B minus B prime. And it is assumed in a naive way, in my opinion, that in a hidden variable world, it's obvious that you can produce such combinations of observables, even though B and B prime are not measurable in a single run of an experiment. So the result of B and B prime, for example, can in principle depend on the order in which these two quantities are measured. Addition is order independent, so that's one indication that maybe something is wrong here. But we'll come to it later. If we make those additional assumptions that these operators have the property that they squared are equal to identity operator, then it means that eigenvalues of A prime, B, and B prime are plus minus 1. And under these assumptions, you can prove the so-called serial sum bounds, which states that possible eigenvalues of the operator C are bounded by 2 square roots of 2 and minus 2 square roots of 2. Now, another look at this problem is that if you square this operator, you can write it in such a nice form, and it shows that a necessary condition for finding this big eigenvalues is non-commutativity of A and A prime and B and B prime. Why? Because if either this commutator or this is 0, then C squared equals 4 times the identity operator. And it means that eigenvalues of C are therefore plus minus 2. So they are smaller, they are in the middle of this segment, so to say, this inequality. So if you want to have something bigger than 2, of course, both of these terms must be non-vanishing. Yeah? But these, as you can see, these are local conditions of non-commutativity. So a necessary condition for violation of the so-called violation of the Bell inequality, which means that for having greater eigenvalues than just plus minus 2, it's local non-commutativity of these observables. So there is certain local aspect which is very important for violation of the inequality. That's what I want to stress. And I will be interested in this local aspect and in all these local properties of these operators from a hidden variable point of view. So I wanted to discuss or introduce some sort of local incompatibility and use this as a single assumption, essentially, that will allow me to violate the Bell inequality, essentially. That's in standard terminology. Well, there's one more thing which I would like to tell you, which I'm not questioning this. So I think that tensor product of observables is a reasonable mathematical representation of a product of observables which correspond to two different systems. So we have one observable measured by Alice, another one measured by Bob. They obtain certain results and they multiply these results. So the result of such an observable should be a product of results of Alice and Bob, and actually tensor products has this property because the eigenvalues of a tensor product are products of eigenvalues, and here in this concrete case, since these eigenvalues are plus minus 1, then it also has eigenvalues plus minus 1. The first point where I think there is a difficulty slightly different from standard textbook presentations of the Bell inequality is here. Namely, these local observables, which I mentioned in the context of this C operator, are 2 by 2 matrices, of course, and 2 by 2 Hermitian matrices. And 2 by 2 Hermitian matrices have at most 2 eigenvalues. Therefore, these operators are binary observables. They have 2 results. You can see here the eigenvalues. So it's plus minus the length of such a linear combination of vectors in 3-dimensional space. Now, so I stress this binary aspect of these quantum observables which occur in this operator C. Now, when you go to the proof of the Bell inequality, the first part is identical, so you make this local step. If you can't make this first step, then you are not able to proceed with the proof, and you are not able to prove the inequality, and therefore there is a possibility that you will find something which violates the inequality, and this is the case actually, and it was known to Bell already. So here we have this kind of expression, nothing new. Now comes the second important argument due to Bell, namely that since b of lambda and b prime of lambda are plus minus 1, then this linear combination can be plus minus 2 or 0. Now if it's 0, it means that signs are opposite. But if signs are opposite, then this is non-zero. And if it's non-zero, it's plus minus 2. Now if this is 0, it means that the signs are the same. But if signs are the same, then this is plus minus 2. So together, this random variable is always plus minus 2, and therefore its average cannot be greater than 2 and smaller than minus 2, and this is the so-called Clauser-Horn-Shimoni-Holt inequality. So this inequality is simultaneously a combination of four averages and just a single average of this random variable, which you can see here, this random variable C. Now, there is a first inconsistency between the logic of this derivation And quantum mechanics, because these random variables, b plus minus b prime, are not binary random variables, but they are ternary random variables because they have 3 values. Yeah? Here we had 2. Quantum mechanically you have 2 values, it's a binary random variable. Here in this derivation you have a ternary random variable, which means that Bell assumes that it is possible to model a binary random variable by a binary random variable by a classical non-binary random variable. And that's how he derives this inequality. Well, I'm interested in a local hidden variable model that reconstructs exactly probabilities from quantum mechanics. Therefore, this proof should not work for some reason. One reason, which I already mentioned, is that it doesn't work if we have a non-local situation, because we are not able then to make this transition from this line to this line. Now, the second situation where it may not work is that these objects are somehow ill-defined. They can be ill-defined because we know that they are ternary, but they should be binary, so there is something wrong with the construction. So how to do it? Okay, but first two morals. So before we continue. So first contradiction between quantum mechanics and Bell-type derivation is that quantum binary random variables are represented by classical non-binary random variables. And second moral is that somehow if we really want to have a local hidden variable theory which reconstructs predictions of quantum mechanics for this concrete situation, for some reason these linear combinations should not be defined. They should be mathematically ill-defined for some fundamental reason. That's the observation. So I want to somehow use some mathematical freedom to make derivation of the inequality impossible because of certain local properties of these random variables. So I want to make it local, the problem, not non-local like in standard derivation. And here we have at least 2 possibilities, which are quite natural from the hidden variable point of view. So the first one is actually what I did in my old paper from 1988, and at that time I thought that maybe since b of lambda and b prime of lambda are functions and somehow these functions should not be added. We should not be able to add or subtract these functions, then perhaps there is something wrong with the domains of these functions. Like here in the example. The overlap of these domains of b and b prime is empty here. Yeah? This function simply does not make any sense. It does not exist as a function because its domain is empty. So it was this old approach of mine, which I found in roughly 2015 and later in some papers which were appearing on the net. The second approach, which is the modern one, so to say, and which is based on my current program, is to manipulate with the codomains. So we can have 2 functions, b and b prime, and they can have the same domain. So it's like we can have hidden variables so that if you know lambda, you know b of lambda and b prime lambda simultaneously. So it's more in the spirit of Einstein-Podolsky-Rosen argument. But then, for some reason, we should not be able to add them or subtract. How come? Well, if their domains, codomains, are incompatible in some sense, then, for example, if they belong to different sets or whatever, some kind of difference, then it may be impossible to add them. But now, of course, the obvious argument is, okay, that's impossible probably because b, the values of b of lambda are plus minus 1, and b prime also has values plus minus 1. So we have plus minus 1 and plus minus 1, and these are the same sets. So how come they are different? But in quantum mechanics they are different, in fact, because we have eigenvalues. If we have eigenvalues of two different Pauli matrices, for example, of course these eigenvalues are plus minus 1. Yeah? So as sets they're identical, but these are eigenvalues corresponding to different eigenvectors. So eigenvalues are the same, but eigenvectors are different. So, and that's how quantum mechanics introduces this incompatibility here. The question is if we can produce something analogous but in a more classical context. Now I'll just give two examples. The first example goes to basically Joy Christian investigates this kind of structure. So the question is if we can have two different pluses, for example. Is it possible to have different pluses? And here plus and minus are just two vectors from a unit sphere in one dimension, in 1D case. And just think of these one-dimensional lines as tangent spaces to some one-dimensional manifold, and we know that now these two pluses, for example, this is one plus and this is another plus, are just two vectors in two completely different tangent spaces. And we know that in order to compare vectors from different tangent spaces, we have to parallel transport them, or we have to introduce a connection somehow. So this is one example, and Joy Christian tries to fight in this area. My approach is different. I will not go in this geometric perspective, so to say. I want to make it arithmetic, which means I introduce something which I call arithmetic elements of reality. What does it mean? Simply, assume that you have two sets, x and y, and they have the same cardinality as reals. The same cardinality as reals means they have the same number of elements as reals. For example, open unit interval 0, 1 has the same number of elements as R. A two-dimensional plane has the same number of elements of R. Cantor set, Koch curve, Sierpinski carpet, Sierpinski triangle, I don't know, whatever. There are sets which have the same cardinality as continuum can be completely different, very strange even, yes. But because they have the same cardinality, then by definition there exists a one-to-one map, mapping one of these sets into another, and vice versa. So there exists a bijection, okay, bijective map, one-to-one map, and such a map exists by definition of the same cardinality, because sets have the same cardinality if there exists such a bijection. Yeah? So if they have the same cardinality, such a bijection exists. And this bijection can be treated as an isomorphism between two types of arithmetic. One arithmetic is just the ordinary arithmetic of real numbers, addition, multiplication, subtraction, and division, we all know. And we can, by means of this bijection, we can define addition, subtraction, multiplication, division in this weird set, like in the Cantor set, for example, or whatever. This strange set. Strange or not strange. Could be x could be also r, and f could be x to the third. It's a bijection, mapping r into r, and so it's okay. Yeah, it's a very good map. So anyway, it allows me to define arithmetic operations in these sets, and since I have two sets, it means I have two types of arithmetic in x, in capital X, and in capital Y. If I have arithmetics, it means I have 0 and 1. 0 is a neutral element of addition, 1 is the neutral element of multiplication. Since I have different arithmetics, I have different zeros and different ones. And these 0x and 0y belong are elements of these sets. So 0x belongs to x, 0y belongs to y. But since these sets can be completely different, like an open interval and Sierpiński carpet, for example, then it makes no sense just to add these two things, because there's no way of adding, just adding a number from a unit interval and a point in a plane. Yes, basically. But so okay, we'll come to it, how to do it. But what's important here, from my point of view, from the point of view of our discussion, is these neutral elements are bits. And they are a little bit like qubits, quantum bits. So here they are not qubits because there is no quantum mechanics here, but I call them projective bits because this arithmetic is called by Mark Borgin, a mathematician from UCLA, projective arithmetic. So let me call them projective bits. And one thing which I find even funny is that these numbers like 0x, 1x, 0y, these bits are determined uniquely if you know ordinary 0 and ordinary 1. Because if you look at this formula, this 0 is just an ordinary element of real numbers. This 0 here is the same 0 here as here, right? This one here is the same one which we see here, but this one is different from this one. So these real numbers behave essentially like elements of reality in the sense of Einstein-Podolsky of Rosen. So elements of reals are elements of reality in this sense, as we can see, as we will see. So we have 0x and 0y. They have a common element of reality, which is just 0 from ordinary arithmetic of real numbers, and yet the sum of these objects may not make no sense completely. But this is one example. I have two sets. X is just r plus, y is minus r plus. So these are positive reals, these are negative reals. I have bijections into r. Here it's just logarithm. Here is logarithm of minus x. Inverse is just exponential function. You can consider here 4 different arithmetics. Even more arithmetics, 5 arithmetics. Because you can have arithmetics in x. Let me call them arithmetics of Alice. You can have arithmetics of y. Let me call them arithmetics of Bob. And you can have this ordinary arithmetic of just reals, standard arithmetic of reals, which we can call the arithmetic of Eve. And you see what happens if Alice adds 2 plus 2. So 2 plus 2 equals 4, which is correct. Yeah? And so this is the result 4 from the point of view of Alice, and this is how it looks like from the point of view of Eve. Now, when Bob adds 2 plus 2, then he also gets 4, but it's minus e to 4 from the point of view of Eve. And the question is, are these results identical or opposite, or exactly opposite? So, from the point of view of arithmetics of Eve and Alice, they are identical. 2 plus 2 equals 4. But from the point of view of Eve, they are different. And one more thing, Alice and Bob can add their numbers. So for example, you can take 2 of Alice and add 2 of Bob and add them by means of such a mixed arithmetic, as I call it here. Yeah? So basically you take these numbers, map them into reals, ordinary reals, then add them or multiply or whatever you want to do, and then go back. That's how it works, essentially. But I think these structures are logically quite similar to what we have in quantum mechanics, this kind of incompatible sets of random variables, which we know from quantum mechanics. Moreover, this kind of mixed arithmetics, you can check that it has many properties of a tensor product. So it's a natural, so it's something in between ordinary product and tensor product in a sense. Now we come to the core of this presentation. If we have arithmetic, which means we know how to add, multiply, subtract, and divide numbers, we can basically formulate calculus. We can, for example, consider a derivative. If we know how to define a derivative, we can introduce an integral. And this integral is something I'm interested in because I will use this integral in formulas à la Bell, or Clauser-Horn, exactly. So you can see here 3 books. This book by Mike Grossman and Robert Katz, it was published in 1972, but they worked on this problem since late 60s. And this is the kind of calculus which is based on this kind of arithmetic which I described. Functions are just functions of reals, ordinary real functions here. Then in 1993, essentially the same idea was discovered by Andre Papp, and he published he published a paper in some local journal. You can find it on the internet today. And this is an example of a modern presentation of his approach by Papp and his collaborators, the monograph from Cambridge University. And here is the book we wrote with Mark Burgin from UCLA, and the interesting thing is that newest one. It appeared in November 2020. The interesting thing is that each of these constructions was done independently. So Andre Papp didn't hear of Grossman and Katz. We didn't hear of Andre Papp and Grossman and Katz when we were writing the book. So at a certain stage we were writing the book where we introduced this kind of calculus which I discovered basically for my own purposes in 2014. And at a certain moment, originally we called this a non-Diophantine calculus because it was based on non-Diophantine arithmetic, and arithmetic is non-Diophantine in the sense that Diophantos from Alexandria formalized arithmetic, like Euclid of Alexandria formalized geometry, so Diophantos formalized arithmetic. So these generalized arithmetics, which were introduced, by the way, by Burgin in 1977, I believe, for the first time, first examples of such arithmetics, of natural numbers, were given by Burgin in 1977. So we called it, as I said, non-Diophantine, but at a certain moment we were just discussing the terminology we are using, and Mark said that in his opinion non-Diophantine arithmetic is not a good phrase, so to say, not a good expression of the idea, because Diophantos, of course, I mean, non-Diophantine arithmetic is okay, but non-Diophantine calculus is wrong in a sense, because Diophantos didn't think of calculus, because calculus is, Newton is responsible for calculus, not Diophantos, of course. So it should be rather called a non-Newtonian calculus, not non-Diophantine calculus. So I just typed non-Newtonian calculus in Google, and after a few seconds I found the book by Grossman and Katz, and the book was just available online, so I looked into it immediately, and then I noticed that practically all the results, all the constructions I have discovered for my own can be found already in the book by Grossman and Katz. So I wrote to Mike Grossman and said, okay, I'm very sorry I found your book, but unfortunately you were earlier. So I will just acknowledge this. I'm sorry I didn't know of your work, so I didn't mention it, but now I will always do it, as I do it now. But fortunately, it was not quite the same as what they did, because they worked with the real line, essentially. Yeah? And I already worked with fractals, more complicated structures, and that's how I arrived at the construction, because I just wanted to have a calculus for fractal applications, basically. So my construction was already based on the idea of this bijection, the same cardinality of sets, and so it's much more general, and in this sense it includes these things as particular cases. What Andre Papp did was also the arithmetic essentially of real line, of the real numbers, ordinary real numbers. What's very interesting from our point of view is that discuss in great detail what they call non-additive integrals. And non-additive integrals is exactly something which I have in this Bell theorem context. So let me, so non-Newtonian integral, which was introduced here, is the one which I'm using, and this is the one which I'm using for Bell theorem, essentially. But in the terminology of PAP, it's a non-additive integral. And these non-additive integrals occur, for example, in fuzzy calculus. So what I do in principle has also some implications for fuzzy modeling. But let me then briefly explain how it works. So let's say we have two sets, x and y, and we have a map A, which maps x into y, and we want to compute the derivative of A. So because of these bijections, which we know exist by construction, all these sets can be mapped bijectively into reals. And therefore, I can write such a diagram. This function A tilde is uniquely defined by A, if we know these bijections, of course. Now, if I want to define a derivative, I just take the most natural definition of a derivative, which is a kind of high school definition of derivative. You just formulate such an expression, take limit delta to 0. But then, of course, x plus delta x must be performed in the domain of my function, so it must be performed here, and these functions must be subtracted here in the codomain, and so here we add in the arithmetic of the domain, but here we subtract in the arithmetic of the codomain. So you have to also divide in the arithmetic of the codomain in the sense of y, and then we have to divide by delta, and this delta has to be carefully defined, so to say. But otherwise, basically, there is no problem, even if these functions f are completely weird. And they are completely wild functions. If you think that x is R3, for example, and you want to map bijectively R3 into R, this function will be strange. It will be discontinuous and so on. But it's not important, it turns out. This function can be discontinuous in the metric topology of x, yet it is always continuous in the metric topology which is induced from the open interval topology of R. And it's enough, it turns out. So it's incredibly general. We don't have to assume anything about continuity, the differentiability of fx and fy here. It's very flexible, the formulas. So we have a derivative. It has nice properties. For example, it's additive in the sense, of course, in the sense of y, because we add values of functions. It satisfies the Leibniz rule, but of course multiplication and addition are again performed at the level of y. But if we know how to compute the derivative, we in principle know how to define an integral, because we want to define an integral in such a way that the fundamental theorem of calculus will be applicable. So under standard assumptions about continuity and so on, we can define the integral. Here, this dr is just standard integration, Riemann-Lebesgue, whatever. Yeah, so standard known from ordinary analysis. This integral is simple and general, basically, and it's so general that, for example, the so-called Hausdorff integral, which is defined for the Koch fractal by Epstein and Schnotycki, this turns out to be a particular case of this integration. Now we can, so it's an interesting. Yeah. So the only non-trivial element here in all these constructions is to find these bijections. If we find them explicitly, then we are done. So it's as simple as ordinary calculus. The only non-trivial element is just to find the bijections. Okay. Now, let me go back to the additivity, for example. Derivative is additive in this subtle sense, in the sense of appropriate arithmetic. Therefore, it's not surprising that the integral is also additive in this subtle sense. So we have this type of additivity or linearity. So you have homogeneity here, and additivity. Now, these forms of standard additivity are not valid here. And it's very bad news for Bell's theorem, because it kills the theorem. It kills the proof of the Bell inequality. Because all the proofs which use this kind of integral representation, at least, explicitly use standard linearity of the integral. Here this integral is linear, but with respect to appropriate arithmetic, not just the naive arithmetic, so to say. And similar properties occur in fuzzy integration. So it's not exotic, this kind of structure. It's known from other branches of mathematics. Now, so we have if you try to build models of hidden variables based on this type of hidden variables and integration, you cannot prove the standard Bell theorem and Bell inequality. You can prove Bell inequality, but all additions, multiplications, and so on must be understood in the generalized sense, not the naive one. Now, it's often stated that Bell's theorem cannot have counterexamples because it's a mathematical theorem, and mathematical theorem cannot have counterexamples. Well, it has. Why? Because Bell's theorem has hidden assumptions. So if we formulate Bell's theorem as a theorem that if we use Lebesgue integration over hidden variables, then okay, I agree that you can prove the theorem, but there is absolutely no guarantee that subquantum world or some other world which will be used to hack a quantum crypto system, for example, is based on Lebesgue measure. Why? For what reason? If, for example, my hidden variables are just fractals, then what do you mean by the Lebesgue measure on a fractal set? But it doesn't mean that you are not able to integrate over fractals. You are able to integrate, for example, you can integrate it in the non-Newtonian way, if you want. Yeah? So, Bell's theorem is a very general theorem, and it's not a mathematical theorem, in a sense, because it's a meta-mathematical theorem, because it's a theorem about reality. It's a theorem about security and quantum cryptography, and not about properties of Lebesgue integrals, because hackers who try to hack a quantum cryptographic system are not obliged to use models based on Lebesgue integration. Why? Why should they use? Maybe Riemann integration or what? No, there's no. This subquantum world or this faking world, which is used to fake quantum probabilities by quantum hackers, can be anything. It can be based on any mathematical structure. So I will give you one example of a structure which clearly gives a counterexample to Bell's theorem. But first, we have a lemma. I don't know if this lemma is known or widely known. Maybe it has some name, I don't know. I found it by accident, in a sense. And the lemma is the following. It tells that if you have a probabilities, basically, yes. We are interested in probabilities. You have this domain and this codomain, 0, 1. Then G, if we require that G of P plus G of 1 minus P equals 1, or G of P1 plus G of P2 equals 1 for any P1, any P2, then this happens if and only if G has this structure where H is an antisymmetric function, and that's it. So it's a very general theorem. Any antisymmetric H will do. And one example, why it's important from our point of view, is that simply, let me take this function, which is a bijection of the unit interval into itself. It's 0 at 0 and 1 at 1. Yeah? We can compute H on the basis of the formula which we had on the previous slide, and we have this function which is clearly antisymmetric. So this must be 1, this combination here, and then it turns out that this combination is just the so-called trigonometric identity, which is valid indeed for any P. So this is one example, and if you take as P the probability of finding a point belonging to the overlap of two rotated half circles rotated by theta, Then you just insert it here and you get cosine squared theta half, and which is the conditional probability typical of spin 1/2. And then, since this is a bijection on the unit interval, you can now continue this bijection to the whole real line just by making copies of it. Yeah? This is an example of a bijection which exactly reconstructs probabilities typical of the singlet state. So I have certain one-to-one map. It's a bijection, therefore, of R into R, by the way. So X, capital X, is just R. And then I can use this bijection to define arithmetic according to this prescription. This one. So I have certain bijection. Here X are just real numbers. So I define a new way of adding natural numbers, real numbers, by means of my bijection. This bijection is constructed as, it looks like this. And since I have this mathematical structure, arithmetic structure, I can introduce my calculus, and therefore I can introduce, for example, my integral. And I obtain these formulas. So as you can see, 0 is mapped into 0 and 1 is mapped into 1. So these neutral elements are just unchanged. So 0 is just 0 and 1 is 1. Here you can see typical Clauser-Horn local expressions for a hidden variable theory. So we have certain integration, certain probability density, which is a number, a constant number here, non-negative constant number. And then you have characteristic functions which are equal to 0 or 1. Yeah? These probabilities sum to 1 in the ordinary way, and as you can see, these here, what you get here are exactly the probabilities from the singlet state, from quantum mechanics. Therefore, you have a maximal violation of the Bell inequality here, and yet you have formulas of a Clauser-Horn type. What else do we need? Yeah? Maybe some comments yet. So these formulas show that in such a generalized framework I am able to write standard local hidden variable expressions for quantum probabilities. And the only difference is that I'm using different type of integration and different type of multiplication. But that's also okay, because in quantum mechanics I also use a different type of multiplication. It's a tensor product. Here I have this arithmetic product, which is, well, okay. This is a sub-quantum world. Yeah? And then I have to comment a little bit on this, but first of all, these characteristic functions. These characteristic functions have the properties of orthogonal projectors. Therefore, the structure of this probability is just a standard structure of a probability with characteristic functions representing propositions. Here, these characteristic functions have numbers, values 0 and 1, because 0 and 1 are unchanged in my arithmetic. So this is just a standard structure. Second important thing which one should understand here is that because of my lemma, I have a probability which can be added to 1 in two different ways. For example, I have P1 plus P2 equals 1, and G of P1 plus G of P2 equals 1. Moreover, I can even say P plus in a generalized sense, P2 equals 1 again. So I have many different ways of adding these probabilities, but what it practically means is that in my set I have two types of arithmetics that coexist, two types of calculi which coexist, and two types of probability that coexist. But since these generalized probabilities add to 1 in the ordinary way, they are consistent with the experimental probabilities. Because what do we mean by an experimental? How we test quantum mechanical predictions, for example. We have a theoretical black box, which is quantum mechanics, which takes, for example, a bra psi, takes a projector and takes a ket psi, and then multiplies them and produces a number between 0 and 1. And this number between 0 and 1 is tested in an experiment in the ordinary way. So we have certain experiments and we count. We count successes and we count trials and divide, in the ordinary sense, number of successes by number of trials. That's how we test quantum mechanics. So at the left-hand side, in quantum mechanics, you would have, at the left-hand side, you would have this experimental ratio. At the right-hand side, you would have something like trace projector row or bra projector cat or something like that. Some abstract formula whose physics is we don't understand its physics. Yeah, but it's not a problem, because what we need is that this abstract mathematical formula produces a number between 0 and 1, and this number is supposed to be obtained in the experiment. If my experiment produces the same number, we said that experiment confirmed the theory. So I have a similar structure. I have a certain abstract mathematical description which applies to the subquantum world in this sense. I have row of lambda, d lambda, I have characteristic functions, all these structures. I have certain multiplication, but in the end, this mathematical black box produces a number which is between 0 and 1. I test this number, and this number is identical to the one produced by quantum mechanics, but so it's tested in experiment, yes? It's positively tested in experiment, but here what is important, I have local hidden variables. Local, you can see locality here in this product, and these classical, so to say, probabilities are here. You have certain, they belong to certain set. In my case, it's just real numbers. And you have certain way of integration, which is okay. Yeah. And you are not able to prove the standard Bell inequality for such a thing because of this difficulty. Because this is the correct mathematics which works at this level. This is simply not satisfied. Therefore, you are not able to prove the Bell inequality or Clauser-Horn inequality or whatever. Yeah, so a proof doesn't work simply for this reason. This proof works, and you will obtain an inequality, which of course will not be violated. But this will not be the Bell inequality. So at this level, you have some other inequality, some other type of Bell type inequality, which is satisfied, of course. Yeah? But if you try to use these formulas, which are not non-valid, then you prove an inequality which does not apply to the model simply. Yeah, so we are here. But one final comment is that since we have arithmetics, we have this subquantum arithmetic, we can basically define any structure and any mathematical structure. In particular, we can define rotations. So we can define the rotational invariance at the subquantum way. This is an example of a rotation in this sense. These rotations for a Lie group with respect to certain parameters alpha, which satisfy some arithmetic, which is irrelevant for us at the moment. And because of this, you can prove that these probabilities are rotationally invariant. They seem non-invariant in a sense, because this is an example of a straight line which is rotated in this way. So for us, they seem strange, but at the level of the hidden variables, they are just ordinary rotations. If I made this plot using the arithmetic of the hidden variable world, it would be just an ordinary rotation of the line. So, from this perspective, what is told us by the Bell theorem, Bell inequality, from this perspective, is a test for the subquantum arithmetic and calculus. So we can make a macroscopic test of microscopic arithmetic. And this microscopic arithmetic is not the standard one we are accustomed to, but we can test it by ordinary experiment, which employ, of course, our own arithmetic because of this formula. Because we will be testing this real number and we will be comparing it with this real number, and the results will be identical. Okay, that's how it works. just to announce further results, I can tell you that the so-called Sirelson bound, which we saw, 2 square roots of 2, can be violated in this framework. It's very easy to deform the subquantum arithmetic in such a way that you will get as close as you want to the Sirelson, to the maximal bounds. For the Clauser-Horn inequality, it's minus 1.5. This maximal left bound. For the Clauser-Schumann-Holt, it's 4. Yeah. So you can get as close as you want to these maximal bounds, still maintaining locality, perfect detectors, free will of observers, and all that. So in my opinion, well, I don't claim I formulated a hidden variable theory for quantum mechanics, because I didn't address this problem. My ambitions are minimalistic. I just wanted to produce an example of a theory, and a kind of toy model, so to say, which satisfies all the explicit assumptions, not only of Bell, but all these modern approaches to Bell, including efficiency of detectors, superdeterminism, and things like that. And yet, I can exactly reproduce the numbers which are predicted by quantum mechanics. In this concrete case, I don't claim I can reconstruct all the predictions of quantum mechanics, which I don't think is true. I don't believe that quantum mechanics should be replaced by a hidden variable theory. That's a different story, so to say. But I'm interested in a slightly different problem, because something which I call a quantum hacking problem is the following thing. If you have a system, a crypto system, yeah, so you have certain system that employs, for example, entangled state quantum cryptography. Can you fake the system by some other system which will produce identical probabilities? So it's a quantum hacking problem. It's more ambitious than quantum measurement problem. So can you fake it? And the standard answer is no, because any system will satisfy Bell inequality, but our system will not satisfy the Bell inequality. Here I give you a formal example of a system, or at least a mathematical model of a system that will reconstruct quantum probabilities, and yet it will involve hidden variables. So in principle, it's subject to an attack. Yeah? So we don't have anymore the proof of fundamental security of quantum cryptography from this point of view. Second objection, again, my formulation is the following. Okay, so give me an example of such a system. I say, I don't know. I don't know it. Maybe someone knows it, but I don't know it. But it's irrelevant. Because, for example, in classical cryptography, the RSA, public cryptography, is not insecure because we know that someone knows the efficient factoring algorithm. No. It's regarded as fundamentally insecure because we are not able to prove that such an algorithm does not exist. Yeah. So the fact that we have to assume that our enemies are more clever than us. Yeah. That's the paradigm of cryptography. So not many people know, but George Boole, the one who introduced Boolean algebra, 100 years before Bell, formulated essentially a Bell inequality. You can call it a Boole inequality. And he called it an inequality for possible experience, which is essentially the same kind of problem. But of course, and if we treated Boole possible experience as an ultimate proof that, well, all probabilities in nature have to satisfy Boole inequality, then we would prove that quantum mechanics is impossible. Yeah. But at that time, if somebody asked, okay, do you know any system that does not satisfy your inequality? He said, no, I don't know it. Therefore, you are secure. No, because 100 years later, we learned quantum mechanics, and it turned out it's a new paradigm, and it does not satisfy the Boole inequality. Yeah? So we are in a similar situation. Maybe in 100 years from today, it will be obvious to anyone that there exist theories which are based on non-Newtonian calculus. simply have no proof. They don't exist, and therefore we lost our proof that quantum cryptography is automatically secure. And this is the main moral of my talk, I think.